So we covered quite a few of the basic mechanics of working through improper integrals in the previous video, and in this one we're going to go on to doubly improper integrals. A doubly improper integral is one that has both of its bounds being improper. Either they're both infinite or they're both asymptotic, or maybe one of them is an asymptote and one of them is infinite. Basically, you've got two things that are wrong with it. And our strategy here is actually going to be pretty simple. We're just going to choose a value that's within the bounds of integration, so something between the two bounds. It does not have to be right in between, just any number between them, and split the original integral into two different parts. Now you should note, each one of those new integrals is going to be improper, and it will require the use of limits to evaluate it. So for this example that I've set below, what's doubly improper about it is that both of the bounds are infinite. So I'm going to choose a number between negative infinity and infinity. I can pick anything I want. I'm going to pick 0 because I think 0 is going to work nicely for me. So I'm going to do the integral from negative infinity to 0 of 4 over x squared plus 1 dx. Then I'll do plus the integral from 0 to infinity of 4 over x squared plus 1 dx. Now each one of these is now its own separate improper integral that I need to work out individually, right? So for the first one, I'm going to do the limit as a approaches negative infinity of the integral from a to 0 of 4 over x squared plus 1 dx. Plus, for this one, I'm going to do the limit as b approaches infinity. I don't want to use a again because I've already referenced a in this problem, so you actually need to use a new parameter, a new constant. 0 to b of 4 over x squared plus 1 dx. Okay. Now I have to evaluate both of these integrals, and I hope you guys recognize that 4 over x squared plus 1, the integral of x squared, 1 over x squared plus 1 is our arctangent integral, so this is going to end up being the limit as a approaches negative infinity of 4 arctan, and then I'm going to evaluate from a up to 0. I think I'm going to just do that right now. So I'll have 4 arctan 0 minus 4 arctan a. So all of this is that first integral. We're going to have all of that plus, and now I have to do the other one, and I'm going to sort of run out of space here, so I'm going to do this thing vertically. The limit as b approaches infinity of 4 arctan b minus 4 arctan 0. So I just need to work both these two things out and then add them together. So first of all, what is the arctangent of 0? That means where is tangent 0? That should happen at 0, right? So I have 0. Then what happens as a approaches negative infinity? What effectively is the arctangent of negative infinity? Okay. So that means when is arctangent approaching negative infinity? So I'm going to sort of think about my unit circle. Tangent, remember, is sine x over cosine x. So when is that thing going to be approaching negative infinity? It'll be approaching negative infinity when we're getting closer and closer to this angle here. Because you'll notice that cosine is 0 but positive, but sine is a negative value, right? So that angle down there is negative pi over 2. So here I'll have minus 4 times negative pi over 2. Right? So the top one ends up basically being 2 pi. Now for the bottom one, we have 4 arctan of b, and b is approaching positive infinity. So if b is approaching positive infinity, it means I still need cosine to be 0, but I need sine to be positive. That's going to be happening as I reach positive pi over 2. So if I have 4 times positive pi over 2 minus the same 0 again, this part of the integral is 2 pi, so we have the original 2 pi and then the second 2 pi. When I add those two things together, my final answer for this problem ends up being 4 pi. This doubly improper integral actually added up to 4 pi. It's kind of astonishing if you think about it. This sort of like infinitely long area can actually have a finite value. It's 4 pi. Cool stuff. When you're doing doubly improper integrals, it is incredibly important that you know that if either one of the two integrals diverges, the entire integral diverges. So if one of them is negative infinity and the other one's positive infinity, even if they perfectly cancel out, the answer is that the integral diverges. Right? So as you're working through these, if you notice that happens, you know that the whole integral is going to diverge if one of the two diverges. So I'd like you guys to work through this one. Like, pause the video, split it into two pieces, do the two integrals, and see what happens. I tried to make this one easy for you guys. So I'm going to do the same thing. I'm going to do the integral from negative infinity to 0, and then from 0 to infinity. Same thing as I did last time. And let me write in the limits right now. The limit as a approaches negative infinity of the integral from a to 0 of x dx, plus the limit as b approaches positive infinity from 0 to b of x dx. The integral of x dx is really easy. It's just 1/2 x squared. So I have the limit as a approaches negative infinity of, let's see here, of 1/2 x squared, so 0 squared, minus 1/2 a squared. So I've got that, plus, now on this other one, I've got the limit as b approaches infinity of 1/2 b squared minus 1/2 0 squared. Right? And so what we're going to find here, imagine as a approaches negative infinity, this thing here is effectively approaching negative infinity. Plus this one over here, as b approaches positive infinity, this is approaching positive infinity. You may be inclined to think, these two things, they might cancel out. This is an indeterminate form. It doesn't matter. To be honest, as soon as this one diverged, we knew that the entire integral diverges. Okay? Now, I chose this problem in particular because I wanted you to be able to see something. And I find this a little bit frustrating, but it's how it works. I just asked you to find the area under this curve, the y equals x curve, from negative infinity to positive infinity. I could totally see how people would want to say that this integral should be 0. Right? What reasoning could somebody give for why this integral should be 0? Like, pause the video and think about that. Well, the reason is whatever area is over here should be the exact opposite of whatever this area is over here. Like, it feels like those two things should add up together to be 0. But the reality is, when you are working with improper integrals, if either one of the two integrals that you had to split it into diverges, it means the entire thing diverges. And that's what we accept. It's the truth, and it's how the definition of an improper integral works.